Hi, my name is Richard Bosse with Yokogawa. I've been involved with combustion controls and optimization for 31 years. In the last 40 years, we've seen a major improvement in internal combustion efficiency in automobiles. 30, 40, 50% improvements in miles per gallon. And largely, that all came out in the 1980s as we moved from carburetors to fuel injection. Now, I contrast that with industrial combustion, where frankly, we've made very little progress in the last 5 decades. If you think about it, we're still dealing with sloppy measurement of air coming in, very little visibility of what the heat value is of the fuel going in. The combustion gases, their response is skewed because we're dealing with tramp air, because those measurements are taken so deep into the process. It's delayed, and the control loops are obviously delayed because all these measurements are coming in so late and have so many problems. And the sad part is, at the end of this, we're leaving the operators with really no visibility, no real-time feedback, whether they're running efficiently or safety, or somewhere in between. Okay, so what has been the net result of all this sloppiness and lack of control? Well, first of all, we're running typically at very unnecessarily high O2 levels and dealing with oxygen swings. There's production losses that come as a result of this. The fuel costs are unnecessarily high. Emissions are at levels that we really don't need to operate at. And then we've created operational difficulties. The units have become harder because they're all over the map. There's coil outlet temperature swings that come as a result of this. And that has implications that are specific to each industry. For instance, in the case of ethane crackers, you're dealing with unnecessary coking. Steam methane reformers, you're dealing with unnecessary aging of the catalyst. In any industry, any fired asset, the tubes are unnecessarily aging because of the expansion contraction. All of this adds up to really an inefficient way of operating, and we haven't changed really, frankly, any of this in the last 50 years. All right, so imagine I'm a production manager and I've got personal KPIs that I have to hit. The expectation is our unit is going to drive down costs. We're going to increase production levels. We've got new targets now for CO2 and NOx. We've got to improve the asset integrity of what we're running. They're expecting the unit to run longer with less damage, less maintenance. And oh, by the way, and most importantly, everybody's expecting all this to run more safely. So how do we get as close as possible to fuel injection for industrial fired assets? 5 critical pieces, core pieces of the puzzle. First of which is to get a real-time heat value of the fuel going in. Especially critical for locations where you're burning purge gas and off gas and refinery gas that's being mixed in. So we get that measurement right before it goes into the burners. Second piece of the puzzle is to get a good airflow measurement, and ideally do burner balancing across all the burners so we know how much air is going in and it's even across all of the burners as much as possible. And that gives us a nice, easy, steady, consistent heat profile across all the tubes. Third piece of the puzzle, and this is probably the newest of the technologies, although this isn't new for us. We've had these tunable diode lasers out for 14 years. That's to measure combustion gases. So we're getting a real-time measurement now as close as possible to the burners of the content of the combustion gas. CO, O2, methane. Now we know exactly what's happening as soon as it's burned. Fourth piece of the puzzle is to make sure that we have the capacity to control this. So we're going to look at your stack damper and any other control devices to make sure that we have very tight control on those. The fifth piece of the puzzle is to make sure that we put this in closed loop control. So we do this by putting a control loop onto your operator's existing screens, and it allows them to very simply turn on or off the combustion 1 mode. So what are the net results of this? Show us the numbers. Well, depending on the fired asset, results are always vary a little bit different. But if you will provide us data in an Excel spreadsheet on any of your fired assets or all your fired assets, we can give you a no-charge estimate on what the throughput increase, fuel savings, and emissions reductions will be if you put in a Combustion 1 solution. I will tell you, we try to target as close as possible to a 1% level, operating stably, safely at that threshold. What do you get out of that? Well, for every 1% reduction in O2 that we can take out of your combustion gas, we typically see anywhere from a 1.2 to a 4.5% reduction in CO2, a 7 to 9% reduction in NOx. The core outlet temperature stabilizes. We've seen up to like a 60% reduction in the variability of the core outlet temperature. There's huge benefits that come out of that. If you've got an ethane cracker, we've measured as high as an 11% reduction in coking. So you can take that either as an extended run but between decokes or an improved operating normally at less coke in your tubes. Finally, while we're in there looking at this Combustion One solution, how it fits your specific fired assets, there's other complementary capabilities that exist in our portfolio. Burner management systems, CEMS systems, turbine control systems. There's a whole slew of complementary applications that will help benefit to make your unit operate better and more safely. So whether you're an ammonia or methanol producer with steam methane reformers, whether you have a dozen ethane crackers out at your plant, whether you're a refinery with dozens and dozens of fired assets, Combustion One has proven, tangible, quantifiable benefits. Less fuel, increased production, improved maintenance, reduced emissions, and most importantly, improved safety at your plant. We'd like to come out and talk to you about Combustion One and the benefits it can bring to your specific fired assets.